In this example, we're going to project y into the subspace W, where subspace W has the basis u1 and u2, which are orthogonal. So u1 and u2 are orthogonal bases, and therefore we can use the formula as before we have learned, and y hat is the best approximation of y on the subspace of W found by this equation over here. Let us try to interpret what does orthogonal projection of y means. If your eyes is here directly on top of y, perpendicular to both u1 and u2. So let's say this is u1 and u2, and your eyes is directly perpendicular to that. So u1 and u2 would create a subspace called W, where we have shaded here, where any vectors in this shaded region can be formed by linear combinations of u1 and u2. When we project y onto the subspace of W, basically y hat will land on W space. We now want to decompose y hat into elements y hat 1 and y hat 2, where y hat 1 is along the direction of u1 and y hat 2 is along the direction of u2. This equation clearly sees that this is y1 along the direction of u1 being scaled by this value. We call them c1 previously, and this is c2, and this is along the direction of u2. So this whole expression over here is y2 hat. What about a visual interpretation of y1 hat and y2 hat? If we look at y hat, as we project y hat onto the line u1, this is y1 hat. If we project y hat along the direction of u2, this is y2 hat. So this interpretation is explained here. The orthogonal projection of y onto y hat of W is a sum of projection of y onto the one-dimensional subspace of u1, u2 up to up. And not only that, u1, u2, up are orthogonal to each other. On the right is an example of one we have is y belonging to R3 and the subspace R2. The subspace W is only formed by two orthogonal vectors. u1 is orthogonal to u2, and they are when they are perform linear combinations of each other, they would get the subspace W. The lingo here is W is spanned by u1, u2. Our problem now is to write y as a sum of vectors in W, or in other words, we are going to decompose y into the basis of W. We can use equation 2 over here, where remember we have u1 and u2 the basis. Here is c1, here is c2, and found by this expression. Please plug the values by yourself. I'll circle them for you. This is u1, this is u2, this is c1, this is c2, and we can get y hat. Once you have found y hat, you can find the error vector, and we call it z in the previous example. This is z. Try it at home. Z is orthogonal to u1, z is orthogonal to u2. You can check by finding the dot product between z and u1 as well as z and u2. Lastly, we want to ensure that we are correct. We plug in z here, we plug in y hat here, and then we should y hat plus z should be equals to y. Now, why are we interested in orthogonal projection? Orthogonal projection not only allow us to calculate easily what is y hat given w. Additionally, the orthogonal projection of y onto the space of w is that it is actually y hat is the closest point in w to y. It means that we cannot find any better approximation of y in w. In the language of math, it says that y minus y hat, which is the error term, is norm. The length of the error term is less than the norm of y minus v, where v is any other point in w. This is a very important theorem. It is called the best approximation theorem. To repeat, it says that by projecting y onto w, by orthogonal projection of y onto w, it is the best point in w to approximate y. Here is a graphical proof of the best approximation theorem. This is y, and this is the space of w. Y hat is the orthogonal projection of y onto w. So we have a right angle here. If we use any other point v on the space of w to approximate y, then its error is this vector over here, y minus v. Compare this to y minus y hat. You will notice that this is the shorter side, this is the hypotenuse, and therefore the length of this error will always be greater than here. This theorem uses the Pythagoras theorem to say that the length of the longer side is the square of the both short sides sum.